Hello everyone and welcome to the first lecture of Inorganic Chemistry, in which we are going to discuss bonding across the periodic table. So to discuss this during the lecture, we are going to cover a sequence of different topics. We will start with reassessing the periodic trends. We will then progress on discussing how do we treat bonding. And from the bonding, we will move into examples of molecular orbital theory. Finally, we will address how to avoid every molecule itself and talk about molecular symmetry. So why would we want to discuss about chemistry across the periodic table and not just what we know? Because you might be tempted to say, oh, well, I've seen the periodic table plenty. I've seen it through my high school. I know it deeply. But when we say that we know it, especially from a high school type of approach, we tend to move from everything we handle relatively confident, which is everything that is also related to organic chemistry, which is hydrogen, carbon, nitrogen, oxygen, stuff like that. Then the ones that do happily nothing, noble gases, we think that they are not going to be reactive, they stay over there, and that's it. Then other elements that are treated usually as spheres with charges, you use them in salt, you use them as ions, but you don't consider them doing other things. A couple of weird ones, phosphorus, sulfur, you might be familiar with them mostly because they appear in polypropylic acids and stuff like that, but everything else is a mystery. And the everything else actually encompasses, if you look at this, most of the periodic table. So what happens beyond our point of comfort? And beyond our point of comfort, there is actually the domain of what we call inorganic chemistry. So anything that is not the carbon, hydrogen, oxygen, nitrogen arrangement that you've seen in high school with organic chemistry, you've seen maybe at courses of organic chemistry, even at universities. There is a very rich chemistry that goes beyond the domain of organic. And it encompasses structure that have the capability of arranging molecules in ways that you would not expect and you could not achieve through organic chemistry. Some examples are available here on the slides, some very fancy, but you can also see that a sequence of them actually demand the involvement of these M's, generic metals, this thing, this is uranium, nickel, cobalt, ceria, something like that. So all of this actually demand the presence of what is beyond the comfort zone to be able to work. And all of this chemistry comes with a very rich sequence of structures, sequence of properties, sequence of type of chemistry we actually want to be able to do, but we must understand differently. So what are we going to do in the section of reassessing the periodic trends? We will section off the problem between what do we know, what does it mean, and what impact is it going to have. So the periodic trends are there for a purpose. They're there to guide you across the periodic table, first of all, to know how big are your atoms going to be. So biggest atoms are going to be over here, the smallest are going to be over there. You have an issue when you start to put ions. The ionic radii don't show here, but those are also roughly periodic. Ionization energy, how easy it is to ionize your neutral atom and exchange electrons around. Electronegativity, that follows. Electron affinity. And there is also this thing in the middle, which is the metallic character, non-metallic character, with those sections that you see sometimes of this is a metal, this is non-metal. It's a very useful tool because it categorizes chemistry from a very broad point of view, and it is an intriguing feature of nature. But even the periodic trends sometimes are more self-intuitive and self-explanatory when you section off the periodic table. So if we forget that there is something else, which I know a lot of students tend to do when they look at the periodic table, and we just look at group 1 and group 2, and then we skip everything, we end up at group 13 with boron, and then 14 with carbon, and we go forward towards the noble gases, you can see this, for instance, the ionic radii are perfectly arranged. You can look at them and very visually even notice how they are perfectly ordered to increase down the period and increase down the group and increase down the period. However, and this is valid for all trends in general, you will notice what happens in the moment you actually consider the whole periodic table. So you stop forgetting there are additional blocks in the periodic table. So if this is the S block, this is the P block, you have the D block of the transition metals and the F block of the rare earths. And yes, the periodic trends are still respected. It is the reason why the periodic table can still be ordered. But you can see that the difference is way less stark. And sometimes you might be tempted to say, well, there is no difference from one into the other. As you go down this line, yes, zinc is way smaller than scandium, but so much smaller. Are we really sure? How small is it going to be? And this is even more so when you consider ions. So even our grasp of periodicity seems to be more complex in the moment we consider the whole periodic table as a thing. Why is that? Because when we say S block, P block, D block, F block, we actually mean what is the orbital of the outermost electron. So the outermost electrons in the S blocks are going to be in an S orbital. In the P block, they are in a P orbital. So that's where your electron configuration wraps up. But the complexity and the beauty of the D block and the F block comes from the fact that the valence ends up involving D orbital and F orbitals, which are shown here with the 3D rendering, which is not really needed for the S, but it is really needed for this type of blocks, right? So if we actually look at the electron configuration, then you have, as I was saying, you have the S going down from 1 to 7s in the S block, the P from 2p to 7p in the P block. The D block goes from 3D, 4D, 5D, 6D down. And then in the F block, you have the 4F and the 5F type block. Why would this bring a difference into the periodic table? Because the orbitals have a different shape, they will have a different behavior, and from their different behavior, what we can see of the atom and how the atom is going to react with the environment will change. So in the S orbital, we actually expect to have no nodes and just this spherical arrangement. This means that the probability of finding an electron is going to be in this spherical region. The sphere increases as you increase the primary quantum number. So as you go down into your group 1, you will find yourself with a bigger and bigger and bigger arrangement, which is the thing that gives you those very big atoms all the way down to cesium. In the P block, you actually have 3 possible orientations. It is not isotropic in space. You will have lobes in the X, Y, and Z directions with a node in between in which you're not supposed to find any probability of getting an electron. The D block and the F block will increase even more the amount of orbitals you're supposed to have. So you will still have directionality of the Cartesian coordinate, but given the amount of nodes that you're able to get with the D, which brings up the angular momentum that your electron can gain, you have some very complex shapes. So you have 5 possible d orbitals that are all, technically speaking, the same in energy, and then 7 possible F orbitals. You can see the complexity of the F orbitals is insane, right? So this complexity comes down to this probability of finding an electron is not as trivial as treating just an S block. And this is something that we have to consider. especially what is very important for when we assess how the atoms will behave and what might be tweaking and making less distinct the periodic trend, we need to consider how far away from the nucleus the orbitals are. Now, I'm showing here a plot that tells you how close are you to the actual nucleus of an atom if you go up in type of orbital. So you go up in principal quantum number, and then at some point you will start to go up in the angular momentum quantum number. So the orbitals are further and further and further away from the nucleus of the atom as n increases. So 1s is going to always be the closest, 2s is further away, 3s is further away, 4f is further away. This is the reason why when you go down all the way to 7s, your atom is increasing in size because the orbital is further away, the electrons are there, and this makes the atom bigger. But you will notice something, which is going from S to P, and from S to P to D, you're actually not increasing the distance. So the principal quantum number will increase the distance from the nucleus, but the localization of this electronic distribution capability, the probability of finding an electron, will get closer, more localized on the nucleus when you go to higher orbital momentum. So your 3s electron will be further away from the nucleus than what the 3D will be able to do. Not because the orbital is not complex, the shape is still there, the complexity of the area of probability, this volume in which you could actually find your electron, stays there. But how big is this area? More complex doesn't mean further away. The D electrons are actually more localized on the nucleus than the P and the S. So if we want to systematize it, this is actually the thing that triggers the Aufbau principle. Why is it easier at some point to put an electron in the next option over, right? So you will always start from 1s, but you will not go directly to 2p, because 2p, by being closer to the nucleus, is slightly higher in energy. So you end up doing 1s, 2s, 2p, 3s, 3p, 4s before 3d, because the energy drops. So this anomaly is actually correlated to this localization of the orbitals, right? And this energy correlation is the thing that correlates with all the other properties. And the fact that the d block, the transition metals, are using the d orbitals will correlate to the fact that the properties and the periodicity appears more flat. So you would have seen this in high school, you would have seen it in more basic courses of chemistry, but this is the actual reason from the orbital point of view. Why do we follow this sequence for the Aufbau principle? So now that we know how do we fill, then the question is, since the atom is never by themselves, the next thing to consider will be the bonding. When you put two atoms together, how do we bond? And from the ranking and basic type of bonds, we tend to use covalent bond, knowing fully well that the more bonds you put together, the stronger the bond is. So a triple bond will be stronger than a double bond, will be stronger than a single bond. But not every bond is covalent. There is also the option of having a bond that is ionic, which will be potentially electrostatically stronger than a covalent. And you have a sequence of weak bonds like the hydrogen bonds. These are only some examples. So you will also find some more detailed things like the London forces if you look through all the possible bonds. But these are very distinct categories. And we just said that given the features in electronic of your periodic table, the shades are a bit more in the gray. It's never black and it's never white. Likewise, the periodic table is full of very broad variabilities of bonds. There are bonds that are fully covalent, but some bonds will be more polarized even while they are covalent. Some bonds are fully ionic, but sometimes as you move across in the periodic table, this ionicity will partially lose the character and either go more towards the metallic type of bond, which is only for elemental metals at this stage, or maybe more towards van der Waal type of bondings. So you do have a bit of a spectrum, and nothing places you necessarily on one end or the other. You can correlate this thing with difference of electronegativity between one atom and the other, but given the full spectrum, you can stay at the corners, but whatever is in between is going to be something that is not one and not the other. And yet, we have the audacity of wanting to treat everything at the same time. So in the next section, now that we reassessed the periodic trends and we know where they come from and we know where something might be a bit more shaded, in the next section, we will actually assess how do we treat the options of bonding in a more comprehensive way.